So in this video, I'm going to talk about sequences, when a sequence converges, when a sequence diverges, and ultimately how to prove those points by finding the limit of the sequence. So let's start off with three different sample infinite sequences. So we've got the first sequence an, starting from 1, going to a half, going to a third, going towards 1 over n, and eventually going towards infinity. Now, another way of defining this sequence is to give it some sort of rule. So I'm going to write this: an equals 1 over n. So if you substitute positive integer 1 as n, you get the first term, which is 1. With 2, you get the second term, a half. With 3, you get the third term, a third. With n, you get the nth term, which is 1 over n. And the second sequence being the sequence of square root numbers, starting from square root of 1, root 2, root 3, going towards root n, and going towards infinity. So bn equals square root of n. The third sequence, cn, being the sequence that oscillates between two values, -1 and +1. So cn equals -1 to the power of n. So for those of you who don't know, these are called sequences. They're basically just list of numbers that follow some sort of rules. To make it easier, you can also imagine sequence as a function f of x, where you input something as x, you get the output. So my question is, what happens to these sequences an, bn, and cn as n tends to infinity? Will the sequence go to a certain value, or will it just go towards infinity and never reach a specific point? Well, to answer those questions, I'm going to need to draw the graphs of each of these sample sequences. So let's do it right now. Nice and straight, I like that. So we've got n as the horizontal axis, an vertical axis. Let's make a few points here. So 1, 2, 3, 4, 5. Perfect. 1. So for sequence an, the first term is 1, so it goes here. The second term is a half, so it goes about here. Third term, a third. Fourth term, a fourth. And fifth term. Okay, now let's draw the other two. Okay, three different sequences, three very different looking graphs. And each of the sequence seems to tend to a different direction. So if you look at the first one, an, as n gets larger and larger, or you can say that as n tends to infinity, the point seems to get smaller and smaller and closer to 0. And we can say that the sequence an is converging, is approaching 0. On the other hand, for sequence bn, as n gets larger and larger, the points also seems to get larger and larger as well. So it's also going towards infinity. And we say that the sequence bn is diverging. And for sequence cn, this is quite an interesting one, because if you connect all these points within the sequence, it kind of looks like the sine graph, right? Which also oscillates between two values. And we say that this sequence is also diverging because similarly, it doesn't approach any certain value, any specific point, and indeed it doesn't have any limit. So, definition a sequence, let's call it AN, converges if it tends to a specific value, let's call it L, as n tends to infinity, and a sequence, let's call it Bn, diverges if it either oscillates or tends to infinity as n tends to infinity. So that's what convergence and divergence of a sequence is all about. But now, how do we determine whether a sequence is convergent or divergent? You do not want to draw the graph all the time, right? There must be an algebraic way of doing this. Well, it's very simple actually. If you look at the definition, it says a sequence AN converges if AN tends to L as n tends to infinity. This L value here is what we call the limit of the sequence. And if you can prove that this L value exists, then the sequence is indeed convergent. Similarly, for a sequence to diverge, you must prove that it either oscillates or tends to infinity as n tends to infinity. So what we're going to do now is we're going to calculate the limit of each of the sample sequences up here and see if the theorem we just made holds. So we've got the limit of n tends to infinity of AN. So now we're just substituting. We just substitute AN as 1 over n equals limit n tends to infinity 1 over n. So we substitute infinity for n and we got 1 over infinity. Now 1 over infinity is obviously 0. Why? Because when you divide 1 by a very large value, the larger the value is, the closer 1 over infinity is going to get to 0, which is exactly what we've seen in the graph of the sequence AN. The sequence converges towards 0. So the sequence AN is indeed convergent. So for sequence Bn equals square root of n, the sequence of square root numbers, and substitute n as infinity, we get square root of infinity. So square root of infinity is just infinity. So this sequence is indeed divergent. And the third sequence, the sequence that oscillates between two values, -1 and 1. Well, this sequence is quite interesting because whatever value you substitute n for, you will not get a different values than 1 and -1. So because this sequence oscillates between two values, we can say that this sequence is divergent. There we are. That's how you determine whether a sequence is convergent or divergent, by finding its limit. So if you haven't understand any detail, any concept, any definition within this tutorial, feel free to scroll back and absorb what I was trying to say, and I'm sure eventually you'll be able to get used to it. That's it for today's tutorial. Thank you so much for watching, and I'll see you in the next tutorials.